discussing methods and codes, and the next few lectures we will look at some case studies from the literature, some interesting applications of machine learning. First, we'll look at applications of machine learning in property prediction, which could be in the form of predicting properties in regression or classifying materials into different classes, and how these can be, or this has been used to discover interesting new materials. And we will also discuss some sort of, it may sound futuristic, but those are very much in the research domain, some sort of next generation application of machine learning to material science, things that are perhaps niche now, but are likely to become mainstream in the coming years. So you should be prepared for that. So with that, in today's lecture, again, yeah. So we showed some examples with neural network last time. I'm not sure if you have tried optimizing the hyperparameters, I mean the architecture of the neural network that I shared with you in the last lecture. But today so today's class we have two targets. One is to get familiar with handling this image-based representation of materials, IRCR, that I had shown you, and then to use that for property prediction. And in the process, we'll learn something called convolutional neural networks, CNNs. So we'll see whether or how use of CNN helps us handle the data, the image data that we have. So yeah, so I'll again hand over this thing to Saurabh. We'll explain both the IRCR and the CNN, and then we'll come back to the discussion.
You can see?
Yes.
Okay.
I hope the screen, I mean, the slides are visible. If not, just type in.
Yeah, visible.
Yeah. Okay, so
Okay.
go ahead.
Okay. So today we'll discuss how we can predict material properties using some image-based representation. And specifically, we'll use this one, which is called invertible real space crystallographic representations, or in short, IRCR. And in the first few slides, I will explain what is IRCR, and then in the next slides, I will discuss how we can use IRCR to train neural networks or other advanced neural network architectures to predict material properties. And also, I will also show how, given some crystal structure data, we can construct IRCR representations. So before going further, let's summarize what is crystal structure representation, or how we can represent it. So any crystal structure can be represented by a repeating unit that tiles the entire 3D space, and this repeating unit is called the unit cell. And the unit cell itself contains a number of atoms that are arranged inside of it. And a material can be represented as a three-tuple A, X, L. So A is basically the atomic species in the unit cells. So if there are n number of atoms in the unit cells, so it will be just A1, A2 to AN. And later on we will discuss how we can encode this A1, A2 and AN. And then second component is X, which is the positions of each atom in the unit cell. So if there are n atoms in the unit cell, so there will be n positions, x1 vector, x2 vector, up to xn vector. And the third most important component is the L, which is the lattice vectors. So there are three Bradley lattice vectors, L1 vector, L2 vector, L3 vector, and also we can express these things, lattice vectors, by 6 numbers, which are basically the lattice heights A, B, C, and angles alpha, beta, gamma between them. Now there are two different types of positions that we can write. So it can be either fractional coordinates or it can be Cartesian coordinates. And we can interchangeably convert between fractional coordinate x and Cartesian coordinates x tilde as following equations. So x tilde, which is the Cartesian coordinates, we can obtain it by multiplying the lattice matrix L with the fractional coordinates x. And similarly, we can get x from L inverse x tilde. As an example, let's say an atom has fractional coordinates 0.25, 0.25, and 0.5. Then its Cartesian coordinate will be x equals to 0.25 times the first lattice vector L1 vector plus 0.25 times L2 vector plus 0.5 times L3 vector. So this slide summarizes how we can represent a unit cell of a crystal structure. And this crystal structure information is basically encoded in some information files. For example, two popular files are OSCAR file or crystallographic information file, also known as CIF. So here I am showing two files for sodium chloride crystal structure. And so this one is the OSCAR file, and you can see this 3x3 matrix is basically the lattice matrix we have discussed. So first row is the first Bradley lattice vector, second row is the second vector, third one is the third vector. And in this line, we are expressing or we are denoting which atoms are there in the unit cell and what is their numbers, how many atoms are there in the unit cell. And then we are writing the fractional coordinates of all these atoms here. And in another file, C file, so instead of writing the lattice vectors, we are writing the lattice sides A, B, C, and the three angles alpha, beta, gamma. And again at the end, you can find the position of each atom, and here we are writing it in the fractional coordinates. So all these files essentially encode the three important informations: which atoms are there in the unit cell, what are their positions, and what is the lattice size. And given this information, we can construct features that we will use to represent materials, and we'll use those features to as input to some neural network or some machine learning models. Now, given these structures, we have already discussed how we can calculate features like composition weighted elemental properties or sign matrix elements or its eigenvalues. Last time we have discussed the sign matrix eigenvalues and also ACSF and SOAP like this. But it is also possible to construct some material representation with this raw crystal structure data, and from which maybe neural network models will be able to extract meaningful features from this raw data. So that, I mean, we don't need to manually create the features, but the model can itself create those features from this raw crystal structure information data. And one such representation is IRCR. So let me go slowly to explain what IRCR is. So let us consider a material up to let's say there are three different type of elements in the material. So this is called ternary material. Let's say the first element is A, second element is B, and the third element is C. Now this representation consists of 5 matrices. E is the element matrix, which encodes which atoms or which elements are there in the unit cell. Second one is the L, which is lattice matrix, and C is the side coordinate matrix. It encodes what are the positions of these atoms. O is the site occupancy matrix. It essentially tells us which atom is occupying which site. And finally, P is the elemental property matrix, which encodes the elemental properties of each atom in the system. Now let's go back to element matrix. Now each element or each atom is represented by one hot encoded vectors representing unique elements up to ternary here, and its length will be Z max, where Z max is the highest atomic number in the database we will be working. For example, here we will be working up to Z max equals to 94. So in our data set there are maximum, we have elements up to plutonium, EU. So each atom can be represented by a one hot encoded vector of length 94. Now, what does this mean? Let's say we have iron and we will place 1 at the position 26, that's the atomic number of iron, and all other numbers will be 0. So in this way, we can represent atoms by one hot encoded vectors. And then lattice matrix will be 2 cross 3 matrix, which encodes in the first row there are lattice sites A, B, C, and in the second row there are angles alpha, beta, gamma. And third one is the site coordinate matrix. Here we will list out all the fractional coordinates row wise, and its size is n sites cross 3, where n sites is the maximum number of sites in the unit cell in the entire database. So in this case, we will consider materials up to 20 atoms in the unit cell, so n sites will be 20. If there are less number of atoms, less than 20, then we will zero pad the other positions. And then there is site occupancy matrix, and there is one-to-one correspondence between site coordinates matrix and site occupancy matrix. For example, here it is row-wise one hot encoded. So here 100 means this is the position. This is the first element. Its position is 0.25, 0.75, 0.75, and then there is one-to-one correspondence between the element matrix. So here 1 means this is the A element. Or for example, here this one represents this row is for the B element, and it's going like this. And the property matrix, so first column is basically the elemental properties of A element, second column is the elemental property vector for B element, and so on. And in this case, we are considering 6 elemental properties, and these are atomic number, electronegativity, period, group, fraction, and valence electrons. You can look at these papers where we have discussed this IRCA representation in great detail. And another important feature of this representation is that this is invertible. So we can invert it back to SIF or POSCAR with no information loss, and hence it is used also, mainly in genetic models. So before going further, let me show how we can construct IRCR. So this is the GitHub repo of this MagGen paper, and if you go to this repo, and there is one folder called generate IRCR, which contains the code how we can construct this IRCR representation using CIF file or POSCAR file. So we basically need 3 libraries: ASC, NumPy, and PyMatGen. And first I have stored the elemental properties in dictionary. For example, electronegativity, I have manually created a Python dictionary to store all the electronegativity up to plutonium. And similarly, I have defining a function to get the group and valence and also period given the atomic number. And with these functions we will use to construct the IRCR representation. We have created a class object called PCI, basically point cloud representation. And you have to specify the file name. So here file is the POSCAR file or CIF file, and you have to specify the Z max. So here Z max is 94, and n sites, that's the maximum number of atoms in the unit cell, is 20. And then you can construct the AC atoms object to extract the informations or PyMatGen structure object, and then using these 2 objects you can very easily get what atoms are there, what is their symbol, and from which you can easily construct the element matrix. You can get the cell lattice size or lattice matrix from this function, and also the atomic positions from this function. And we have also written this how to get the site occupancy matrix, and finally property matrix. And if you want to encode more than 6 properties in the representation, you can add up other lists for those properties, and finally you have to add up all those properties here for each element, and finally you can get this using this function you can get that representation. So you can look this code, and then once this part is ready, you have to load the zip files to some folder. For example, here in my case, I have loaded all the zip files. So you have to iterate over all zip files, call that PCR class, from that get PCR underscore new code, and you can, from this line, PCR equals to capital PCR, you have to put the compound, you have to give the values to Z max and insights, and it will create that IRCR representation. Now, once this representation is ready, so let's what will be the size of this IRCR? So in our case, Z max is 94, insights is 20. So IRCR shape will be 144 cross 3. Now our first task is to predict the formation energy using neural network with this IRCR representation. Now, so first we have to flatten this matrix to a vector. So in this case, it will be a vector of length 432, and we will pass this vector to a neural network. So this is multi-layer perceptron. So in the input layer, there will be 432 neurons. So this structure I have discussed in the last class. There will be multiple hidden layers, and finally there will be output layer. So the training data of which I have used is taken from Alexandria database. It's a curated data from that, and we have used 15,130 materials. So I have built a neural network architecture with 4 hidden layers. This is exactly the same code I have discussed last time. So let me reiterate it again. So there are input size will be 432, and then I have used 4 hidden layers. So in the first hidden layer, there is 1024 neurons. In the second hidden layer, there will be 256 neurons. In the third hidden layer, there will be 128 neurons, and finally in the fourth hidden layer there is 32 neurons. And after each layer, it will be passed through batch normalization, and I have used ReLU activation throughout. So the standard order will be this for each layer. So first it will be passed through linear layer, then it will be passed through batch normalization, and finally it will be passed through ReLU activation. So given the input X, it will process like this. So it will pass through linear layer, pass through batch normalization, and then pass through activation function. And it will be passing through all those 4 hidden layers, and finally the output will be passed through the last layer. And I have used a batch size of 256 and learning rate 10 to the power minus 4. And I have trained up to 200 epochs. You can see the learning curve. And so should I discuss how I have trained it? I mean, last time I have discussed that code. It's fine. Okay, so up to 200 epochs I have trained. I have trained it in GPU, and it took 20 seconds. And you can see this is the parity plot. It's much better than the last time because the data set is much larger, and also there are a lot of informations. So in the training set, the mean absolute error is 0.026 EV per atom, and R2 score is 0.995. And in the test set, the mean absolute error is 0.101, and the R2 score is 0.946. So it's doing better than the previous model actually, and although we have obtained a very good performance, there are still certain limitation of this architecture because the way we have handled the data. So before feeding this information to the neural network, we have flattened this matrix because that's how the neural network can process that data. It can only accept vectors. But because of this flattening, we have destroyed the spatial structure. I mean, this IRCL is a matrix. I mean, you can think it as an image. So each image is like a matrix. So for example, these are handwritten digits, which are matrix of, let's say, size of 28 cross 28. And now there are specific structural features you can see. I mean, which is obvious for images and not obvious for this matrix. So there are specific patterns or semantics for these handwritten digits. So if you flatten it, you have destroyed the spatial structure. So for example, a pixel at some particular position xy, it will lose its connection to its neighbors and destroying the local context like shapes or textures. So a better approach will be using something called convolutional neural network on top of our LP. So what is convolutional neural network? And CNNs, actually, it automatically learns spatial structures of features from data using a particular operation, which is called convolution operation. And how does it work? So convolution, in each convolutional layers, the architecture apply learnable filters that slide over the input to detect edges, textures, shapes, or any complex patterns in the data. So this image demonstrates how convolutional operation works in CNN. So for example, here we have an image of size 6 cross 6. Now there is a filter whose size is 3 cross 3. So this 3 cross 3 filter scans this entire image at each position. At each position, it performs element-wise multiplication with the selected patch. For example, here selected patch is this one. Within this red boundary. So this is the selected patch and our filter is 3 cross 3. So at the first operation, it performs element-wise multiplication. So 4 will be multiplied with 1, 9 will be multiplied with 0, 2 will be multiplied with -1 and so on. And at the end, you have to add up all these numbers to get the feature value. So this is 2 in this case. And at the end of this operation, you have to move this filter towards right. And how much you will move, that will be determined by a parameter which is called stride. Stride means the number of pixels by which the filter moves after each operation. So here stride is 1. That means after this operation, the filter will move just 1 pixel value. So the next patch will be this one. And again, you have to do this element-wise multiplication and then sum over all these numbers, you will get the second value. So in this way, you can scan the entire image with a single filter. And again, I mean, you have to specify how many filters you want to use in your code. So number of filters and also the number of and also the size of this filter are hyperparameters that we have to optimize. So this example shows how the first and second output values are obtained, demonstrating how convolution operation extracts local patterns from the image. So after scanning through the whole image, we will get a feature value. And another important thing is this: we can control or we can change the stride value, and by changing it, the filter jumps more pixels at each step, which reduces the spatial size of the output. So in this way, by changing stride, we can also control the size of the feature map. So we can downsample the image also. So this is one particular architecture, an example of convolutional neural network. So here is the input. you have to perform several stacks of convolution operations depending on how many channels you have or how many filters you are using. And there is another operation you can do additionally to downsample the image, is called pooling operation. So pooling reduces the spatial size of feature maps that we have obtained from the convolution operation while keeping key information. And the more popular pooling operation is max pooling, where we select the largest value in each small region. So for example, if we select this is the patched region for pooling operation, for the next feature map, the value will be the maximum value of the pixel here. So in this case, 9. And for example, here or here it will be also 9 for the pooling operation. So essentially, pooling downsamples the feature map and it makes the model more efficient and more robust to small shifts. And you can reiterate these things so on. So for example, convolution pooling, and at the end you have to flatten the final feature map. So, and this flattened vector will be passed through some MLP, and either you can do classification or we can do regression. So essentially, convolution operations extract the feature from the raw data, and at the end we have to flatten that feature map. I mean, it's already learned, and there are a lot of semantics or structural correlations we have already extracted. So at the end, this flattening, I mean, doesn't destroy that correlations in comparison with the flattening at the beginning. So now for our particular IRC representation, so its shape is 144 cross 3. So it's not typically like image size. So image sizes are basically square size, 28 cross 28 or 36 cross 36 like this. So when the matrix will be square size, for example here, this is a square matrix. So for square matrix, you have to perform the convolution operation in 2D plane. So the filter will go right way, I mean horizontally, and also the filter will go downwards vertically. But for our particular case, in this IRCR, there's no space to go horizontally. So we will first use 1D convolutions. So the convolution operation will be working in one dimension, which is vertical directions. So this is the particular architecture we will be using to predict formation energy using these IRCA representations. So first you have to write a convolution block. So I have used here 4 convolution blocks. Now what is convolution block here? So the first operation is nn.conv1d. So this is 1D convolution in PyTorch. So there are several arguments. So in C is the number of input channels. Now here 144 cross 3, we will treat the second dimension 3 as the number of channels. So in the input channel is 3, and 144 we will treat this as our feature map size. So input channel is 3, and then you have to specify what will be the output channel, and then you have to specify the kernel size or filter size. For example, the example I have shown, the filter size is 3, and you have to specify stride, and also additionally there is one parameter called padding if you want to pad the outer layer of your image. So first you have to use this convolution layer, and then the feature map will be passed through some activation function, and finally it will be passed through batch normalization. Now in the neural, I mean in this case, I have used leaky ReLU activation function with a parameter of 0.2. And how it will process, given an information x, first you will do the convolution operation, pass it through the activation function, and then finally pass it through the normalization layer, and you will get the output. So here I have used 4 convolution operations. So in the first convolution operations, it will, since there are 3 channels, so I have used 3, and then these are the hyperparameters. So I have used output channel to be 64, I have used kernel size or filter size 5, I have used stride 2 and padding 2. So you can calculate what will be the output shape here. So the input shape is 144. Because of the stride 2, this 144 will be half. So it will be 72. So that's what downsampling is working here. And then the output channel is 64. So the final shape of the feature map after the first convolution block will be 72 cross 64. And then this feature map will be passed to second convolution block. And again, I mean, its input channel will be 64, and we have specified the output channel to 128. We have used the same number of kernel size 5, stride 2, padding 2, and you can calculate what will be the feature map after second convolution. So 72 will be half to 36, and the output channel is specified to 128. So after convolution 2, the feature map size will be 36 cross 128. And similarly, convolution 3 and convolution 4 is there. So after convolution 4, the feature map size will be 18 cross 256. And then we have to flatten this feature map. So after flattening, the size of that vector will be 256 cross 18. And again, we have passed it through the same MLP we have used in the earlier tasks. So there will be linear layer and followed by batch normalization. And for the entire network, given the IRCR X, first it will be passed through the convolution layer. So there will be 4 convolution layer, con 1, con 2, con 3, and finally con 4. Then flatten it and then pass it through the fully connected layers. And first linear layer, then batch normalization, then activation, and you will get the output. So these are the I'm comparing the model performances here. So the first row is for the MLP, which I have already shown, and the second row is for the CNN architecture that we have built now. Now you can see, if you look at the learning curve in the CNN, after 200 epochs, the loss reaches to 0.1, but in MLP it will be roughly around 0.15. And parity plot looks same. It's difficult to distinguish, I guess, almost same. But if you look at the performance metrics, for example, in the test set, you can see the mean absolute error is 0.086 and R2 score is 0.958. And visually it will be clear, it is clear that for the MAE, the MLP has a mean absolute error of 0.1 and it decreases for the CNN. So CNN is doing better here as we have anticipated. And for R2 score, the R2 score increases for CNN with respect to the MLP from 0.946 to 0.958. So in this, in these examples, I have demonstrated how we can use IRCR as the input to train multi-layer perceptrons to predict formation energy, and then how we can use CNN architecture on top of that MLP to increase the model performance. There is one limitation here of this representation. I mean, it's doing great, but one limitation is this representation is not invariant to translations, rotations, or atom permutations. I mean, the representation of crystal structure should be invariant to those operations, because if you do those operations on the crystal structure, the material properties will change. But here, if you rotate the crystal structure, this representation will be changed. So this is one limitation, and to overcome that, you have to do data augmentation. I mean, like in the training data, you have to consider several rotated, translated, and permuted copies of randomly selected some fraction of structures, and then the model will be able to learn those invariant properties. Yeah, that's it from my side today.
All right. So what you saw was application of an image-based representation of materials for property prediction. But interestingly, these image-based representations can be used for other more advanced purposes also, which is beyond the scope of what we can discuss in this course. As I had mentioned, so there were two kinds of features that I was talking about when I discussed the basic materials features. One class was the local features, the other class was the global features. And I had mentioned that these image-based representation, this particular one, for example, IRCR, is a global representation because you are representing the structure of the entire crystal. But it's very different in spirit compared to having to construct either sign matrix or Ewald matrix or ACSF or any of those quantities. You don't need to really calculate anything. Given the structure of the material in the form of a C file, JSON file, anything, postcard file, any which way you have the material structure and composition, you can simply rearrange that information in the form of this IRCR. And then you can use a neural network and maybe neural network plus CNA for property prediction. So we will share this from SIF to IRCR code is also there in your GitHub page, right?
Yes.
Yeah. So we'll share the GitHub page, and it's all public, and I would recommend that you use that, try it out, and maybe you would, I don't know, you may find it useful in your project also. So,
and also these codes I'll share also.
Which one?
I mean, this neural networks code.
Yes, we'll share the neural network code as well and the slides. Yes. So that more or less concludes our discussion on property predictions.
We'll wait for Professor Singh.
No. So he
Oh.
somehow got disconnected. Thankfully,
Oh, yes.
Saurav is here today, so I'm using his computer. So we have more or less completed our discussion about property prediction, etc. As I said, the next few lectures we'll do more advanced applications, some use case of these things from the literature, and also more advanced applications. And then let me announce that the last class, that is on the 12th of December, we'll have the final presentations, which will be live presentations. And by next Monday, those who have submitted project ideas, by next Monday, they have to submit the midterm progress, the videos. Yeah. Anything more you would like to add, Shubhankar?
Nothing for now. I think we did not hear that thread of email chains. Now at least is the time so that you can engage with us. Yeah.
Yes.
Saurav is here, who is an expert in this field now.
Absolutely.
And you use him till he is here. Please use him. So please write us emails. Yes, that's what I'm saying.
Okay. So we'll wait for a minute if there are questions. If not, we'll close today's session and we'll join again on Monday.